Welcome. In today's class, let us continue looking at multiple driving forces resulting in a flux of a certain kind. Okay. This is the first example that we are going to look at in some detail, and this has significant applications, or it has great significance for the human body, otherwise, and so on and so forth, as you'll see when we go through today's class. This is on simultaneous concentration gradient and electrical potential gradient, and we are going to look on the effect of these two simultaneous gradients on mass transport. Let us first understand, or we need to understand, the principles that govern the mobility of ions in solution, or the way we understand it to provide us with some strong base, we need to be clear about it. Some of this you may have seen as final equations in your previous courses, classes, and so on and so forth. Here, we'd look at it from our point of view. We'll try to understand it from our requirements and so on. Let us consider a system consisting of charged species or ions, and we are going to place that in an electric field. That's the situation here. Then the ions will experience a force due to the electric field. Okay. We have already seen in the one of the previous chapters, electric charge flux, how this could happen, the disruption of the cloud and so on and so forth. You can go back and verify that. So these ions will experience a force due to the electric field that is placed over this setup, our system, let us say. That force will result in an ion flux in the medium that comprises the system. So there is a certain medium in the system, and these ions are in the medium, and the electrical force or electric field that is applied will result in an ion flux, or could result in an ion flux in the medium. In such a situation, the species velocity of ions, recall our mass flux, how we talked of the velocity of a certain species, rho I vi, right? You recall that? Okay. Here, we are talking of species velocity of ions, which are charged particles, charged molecules, whatever. We are going to write the species velocity of ions as a product of the force on a mole of ions, that is Newton per mole, which is represented by a certain F, times something called a molar mechanical mobility. Okay, this is a new term, molar mechanical mobility. The developments have taken place on the basis of this term, and therefore we are going to also develop our things on the basis of this term. So the units of molar mechanical mobility are quite complex, as you can see. You can back things out, then you'd find that molar mechanical mobility has the units of mole meter per Newton second, okay, and is usually represented by the symbol U. We are going to use the symbol U for the molar mechanical mobility in this course, and the symbol F, lowercase f, for the force on a mole of ions. The flux due to the electric field, the molar flux due to the electric field, which we are going to represent as Je star. In one direction, we don't worry about the vector, but it is actually a vectorial quantity. So the flux due to the electric field, Je star, is nothing but the product of concentration into velocity. We have already seen this. This velocity, the species velocity, is written as a product of the molar mechanical mobility and the force on a mole of ions. So Cu, F, is going to represent our flux, the flux of ions due to the electric field. The E represents the electric field. Let us call this equation 6.1.1-1. Now, we are going to consider the work done in this context. Okay. let us try to understand the various ways of looking at work. You may be familiar with some of these, you may not be so comfortable with some of these. It's good to make sure that we understand this clearly. From a usual mechanical viewpoint, physics viewpoint, work done is force times distance. Okay, or classical physics viewpoint, work done is force times distance. From an electrical viewpoint, work done is charge times potential difference. We all know this from our higher secondary school, high school. The work done in an electrical system is the charge times the potential difference. The work done is the same, it's just the view that is different. Either you look at it from a mechanical point of view or an electrical point of view. Since the work done is the same, we are going to equate the two viewpoints here, because this is a system with charges and electrical aspect. So force times distance equals charge times potential difference, right? We are equating these two right hand sides here to get force times distance equals charge times the potential difference. So force, if we divide both sides by mole and take that along with this, force per mole times distance equals charge per mole times the potential difference. Therefore, the force per mole that we've been talking about is nothing but charge per mole times the potential difference divided by the distance here. And what is this? Nothing but the potential gradient. So force per mole is charge per mole times the potential gradient here. Now, if the particles are charged with a valence Z, it has a valency of Z, and the electric field intensity is given as minus del of V, where V is the electric potential, this we have already seen. The force on a mole of particles, okay, force per mole, force on a mole of particles, which we said we will represent by the lowercase f, is nothing but minus Zf del V. Okay. So, if you want to write this in one dimension, you could write this as minus Zf dV dx. Okay. If it's a one-dimensional case, we could write it this way. And this is a three-dimensional case. In a three-dimensional case, you write it this way. Let us number this as 6.1.1-2. And this is nothing but E, right? The electric field intensity. Therefore, the force per unit mole, or force per mole, force on a mole of particles, is nothing but ZFE, which is represented by the lowercase f. F is called the Faraday's constant, as you all know. Okay, note where it comes about. It's the constant of proportionality between ZE and F, right? The force on a mole, you divide it by the valency times the electric field intensity. That's the Faraday's constant. Okay, this is significance. Just make a note of this. So F establishes the equivalence between chemical and electrical basis of looking at a flow of electrons, let us say, because the flow of electrons is typically considered current in the classic electrical concept. And of course, you could also have a chemical view on things, mole and so on and so forth we have brought in. So both of those things go together here. F essentially establishes the equivalence between the chemical and electrical basis of looking at a flow of electrons. Okay, that's it. We will strengthen that as we go along. From a chemical point of view, a flow of electrons is considered current. You all know this. Hence, the flow of the number of moles of electrons per unit time can be a unit of current, okay, or unit for current. From an electrical point of view, the amount of charge per unit time is taken to be current. We know this. We have defined it this way, I. Thus, the equivalence is electrons per mole times charge per electron. Okay. So, this is nothing but this is the number of electrons per mole, you know, that's the Avogadro number, 6.023 times 10 power 23. and charge of the electron is a constant, physical constant, 1.6 into 10 power minus 19 units, okay, coulombs. And therefore, the Faraday's constant is 96,487 coulomb per mole. Okay. So remember this constant, it's a nice constant to remember. You probably already remember it. And this is the basis for the Faraday's constant. It essentially establishes the equivalence between the chemical and electrical basis of looking at a flow of electrons or looking at current. Here we are looking at the movement of ions, movement of charged particles, and therefore we need to understand this. Now if we substitute 6.1.1-2 and 6.1.1-1, what are those? This is 6.1.1-2, which gives us an expression for the force per mole of course per mole is in as ZFE, and 6.1.1 is the expression for the molar flux in an electric field, CUF. Okay. So we are going to substitute for F using ZFE, and if we do that, we get JE star due to the electric field. Okay, this E represents the electric field, is nothing but Cu Z F dV dx. Okay, we have substituted for the force per mole in terms of U and C and so on and so forth, and therefore we have this. Okay. So this considers only the electrical driving force. Normal diffusion is always present. Okay, as long as there is a concentration gradient, diffusion, mass diffusion will be present. There's you cannot avoid that at all, as long as there is a driving force for it. So normal diffusion would also be present because it results from collision between molecules by virtue of thermal energy. And as long as you don't reach absolute zero, this is definitely going to happen. That would result in a flux of charged particles when there is an appropriate concentration gradient. Okay. So since you have a concentration gradient, or if you have a concentration gradient in these systems, in addition to the electric field that is imposed, then you have motion due to both an electrical driving force as well as a concentration gradient driving force. Okay. So that's the situation here. So the flux for the nth ion, remember our equation 6-1, it said that a flux is the sum of the vectorial sum of fluxes from the different driving forces. We talked about concentration gradient, electrical, C, E, and then P, a pressure gradient, and T, a temperature gradient, and so on and so forth. Okay. So from that equation, for the flux for the nth ion can be written as Jn star, the molar flux here, therefore a star, Jn star, a vector, is nothing but the sum of, vectorial sum of the Jnc star due to the concentration gradient plus Jne star due to the electrical potential gradient, okay, or an electric field that is set. Electric field intensity is nothing but the potential gradient, right? We know that. Therefore, let us substitute the terms. We know that the concentration gradient flux is given by Fick's first law, minus dn, dc, and dx, one dimension for us to understand things, and then we'll extend it to 3 dimensions. Minus this expression here for the nth ion. So Cn, Un, Zn, F constant, dV dx. So this expression, which is equation 6.1.1-3, gives us the combined effect of a concentration gradient and an electrical potential gradient on the mass flux of the nth ion, the molar flux of the nth ion. Okay. Now using the Faraday's constant, the net charge flux, which is also called the current density, we don't use this term, net charge flux, In dash, which is the charge per time per unit area, regular flux, right? We are now comfortable with it. Can be related to the net mass flux of the charged species, that is amount per time per unit area. Net mass flux of the charged species, Jn star, as Znf Jn star, right? So this is the charge per time per unit area, right? So we have used the Faraday's constant and converted this flux, the molar flux, into the current, right? That's essentially what a Faraday's constant gives us also. Converts the movement to electrical terms. In this case, here we are used to represent it as the charge per time per unit area. Equation 6.1.1-4. Now, if you substitute 6.1.1-3 into 6.1.1-4, what is 6.1.1-3? It was this, where you have a combined expression for the molar flux of n. If we do that, then In dash, the charge flux, is nothing but, there was a minus there already in the previous expression, 6.1.1-3, and therefore you get minus, Znf remains the same. For Jn star we substitute, Jn star we substitute the minus dn dCn dx plus Cn un Znf dV dx. 6.1.1-5. Now 6.1.1-5 gives us the net ion flux, okay. Always it is net, it is a vector. There could be some in this direction, some in this direction, but it is a net that we are concerned with. So the net ion flux, when diffusion as well as mobility in an electric field are operational. And this equation, which gives us the net ion flux under these conditions, when diffusion and mobility in an electric field are operational, is called the Nernst-Planck equation. Okay. So you may, I'm not very sure whether you have come across this. You would have come across some other equation, which we'll see later. This is called the Nernst-Planck equation. A relationship between ion diffusivity, d, or dn in this case, and molar mechanical mobility has been provided by Einstein. He did a lot of work on these aspects. He has provided us with a relationship between ion diffusivity and molar mechanical mobility, which we will directly use here. Okay, we are not going to get into how that arises and so on and so forth. If you are interested, you can go back into archives and take a look at those original papers to see. But here we are just going to use the relationship between ion diffusivity and molar mechanical mobility that was provided by Einstein, or Einstein's relationship. Einstein's relationship is rather simple looking. dn, which is the diffusivity, is nothing but the molar mechanical mobility. See, this thing comes in this formulation. That's the reason why we have been developing things in terms of the molar mechanical mobility. So diffusivity equals the molar mechanical mobility times RT. That is the relationship, Einstein's relationship. Therefore, okay, let us number this 6.1.1-6. And substituting this into the previous expression, the net ion flux of the nth ion equals minus Cn un Znf times RT by Cn. Instead of dn, we are going to write it as RT. When I pulled out a Cn also here. So RT by Cn comes in here in the place of dn. And of course, you have a Znf dV dx coming in because I pulled in extra terms out. Okay. So you can verify this. Okay, let me just go back to this equation to show you. You have minus Znf dn dCn dx plus Cn un Znf dV dx. Okay, I'm going to pull out all this Cn un Znf. So that is okay, f. I think we're going to leave here because we already have f here, and I think we're going to leave the Zn here. Let's see. Cn un is definitely going to get pulled out, and therefore this becomes dn by cn un. And then we are going to use the d equals un times rt to replace the dn here, and therefore we get in dash equals minus cn un zn f rt by cn dcn dx plus zn f dv dx. This can be written as minus cn un zn f. Now, if you look at this, this is dcn by cn. There's nothing but d ln cn, right? Or you could, d ln cn. And therefore, you could write this as d ln cn dx plus zn f dv dx. And therefore, if I pull out this, take the derivative over a combined term, sum of terms, therefore I can do that. Therefore, d dx rt ln cn, that has been modified into d ln cn, plus zn f times the potential gradient, which is being represented by, this is the same v, potential gradient here. The d dx has come out here. So 6.1.1-7. At electrodiffusive equilibrium, electric field, diffusive concentration gradient. At electrodiffusive equilibrium, what does equilibrium mean? That movement in one direction equals the movement in the other direction. It's a dynamic equilibrium always. Therefore, there's a movement in one direction, there's a movement in the other direction. We don't deny that at all. Only thing is that the rates are matched. Okay, that's what equilibrium is. The net fluxes of all ions are zero. That's the concept of electrodiffusive equilibrium. Therefore, this net ion flux in dash has to be equal to zero. Okay. So note this. So this is the way we are going to represent the electrodiffusive equilibrium. In dash equals zero. So if you substitute in dash equals zero, you could directly write this. You're going to pull out more common terms. Cn un, we're going to pull out another Zn, therefore we need to divide this by Zn. This becomes Zn squared. We're going to pull out f also, and therefore you need to divide this by f. The f that was here came out. Both were constants, therefore we could do that. And so minus Cn un Zn squared f squared d dx of rt by Zn f ln Cn plus v equals 0. So this is the condition for electrodiffusive equilibrium. Now, okay, let us number this as 6.1.1-8. If this is equal to 0, then the only way this can be equal to 0 is that if either this is equal to 0 or this derivative is equal to 0, right? That's straightforward. It's a product of two terms. Let us examine how this could be 0 or whether this could be 0. Cn cannot be 0, okay, because Cn is not equal to 0, because the 0 value implies absence of particles, meaningless situation. Un cannot be 0 because the 0 value implies that the particles are fixed, no molar mechanical mobility, which means the particles are fixed and cannot diffuse or move in an electric field. That's meaningless again here. Zn, of course, cannot be 0 because the 0 value implies uncharged particles, which is again irrelevant here. F is a Faraday's constant, certainly not 0. Okay. So this term cannot be 0, which means if this has to be equal to 0, electrodiffusive equilibrium, this term alone can be 0. Now, let us examine this further. This is equal to 0. Now, this is a derivative, right? So we all know that the derivative of a constant equals 0. So this could be a constant. Okay, don't be so confident. This could be a constant, maybe not. We'll see. If this is a constant, what does it mean? It means a meaningless situation. Okay, what I want you to do is pause the video here and go term by term and figure out why this cannot be 0, or the argument of this derivative cannot be 0. It cannot be a constant, not 0. It cannot be a constant. Okay, so think about why this cannot be a constant? Take a few minutes, pause the video, think about it. Go ahead, please. I'd let you figure out why this cannot be a constant. If this is a constant, it leads to a meaningless situation. Okay, think about it. If you cannot get to the answer, raise a question in the forum. We'll discuss things there. Therefore, the only way by which this term would be 0 is that the argument itself is 0. The argument itself can be 0. This is the sum of two terms only if this term cleanly cancels out this term, right? In other words, d ln Cn dx equals minus Zn some beta, which is a combination of terms. I'll tell you what it is. Zn beta dv dx. So this is the only condition that is possible. Beta turns out to be f by RT. You can work out the algebra and find out that this is indeed the case. Just transposition, nothing else. And of course, taking the derivative. We'll call this equation 6.1.1-9. And if we integrate this expression, we get Cn equals Cn naught. You have d ln Cn dx. Therefore, you get an ln, and therefore you get an exponential on this side after integration. And you take the constants of integration, get the Bessel values and so on. Then you'll get Cn equals Cn0 exponential of minus Zn beta V minus V naught, where this stands for the potential. Okay. Equation 6.1.1-10. Have you seen this earlier in some form? Hold on. The subscript 0 indicates the point of reference for the potential, right? Okay. We get, if we transpose this, V minus V0 is nothing but we're going to go back to RT by F. So minus RT by Znf ln of Cn by Cn0 or Cn0, okay, or O or 0, whatever it is. Have you seen this equation earlier, which you got from this? I'm sure you have. This is the, before I tell you what it is, let me number it, 6.1.1-11. This is the Nernst equation. I'm sure you would have heard the term, you would have seen the equation. I'm sure you recognize this equation, Nernst equation. And this is a very useful equation. We are going to use it again and again. At electrodiffusive equilibrium, the spatial distribution at electrodiffusive equilibrium, the spatial distribution of potential is proportional to the logarithm of the solute concentration. You know that the ln A minus ln B is ln of A by B. Therefore, this is actually ln A minus ln B. So, at electrodiffusive equilibrium, I dash equals constant. The spatial distribution of potential is proportional to the logarithm of the solute concentration. This is essentially the meaning of Nernst equation. Okay. I think we need to stop here. We have been at this for some time now. I think it's best to stop here. New information. Therefore, I'll let you process it and let us continue in the next class. See you.